Hi guys, welcome to Learn Extra, Grade 12 Physical Sciences. My name is John and I'm here today with Philip. And Phil, what are we doing today?
We're doing some organic reactions. We're going to be taking a look at the chemical properties of some of those organic chemicals we were talking about, and I hope you're going to join us.
Okay, so I guess that means we're doing addition, substitution, elimination.
And combustion too.
Okay, combustion as well. Great guys, now remember this is critical stuff. It's foundational, and you know what? It's the easy stuff for paper 2. You can get lots of marks and you can do really well. So join us, get onto Facebook. I'll be watching the page. Unfortunately, Indy wasn't well, so she had to leave us. So I've stepped in just to watch the page. Our address on Facebook, facebook.com/learnextra, and on Twitter, it's at Learn Extra, and we're going to go to a short break. I hope you've been inspired by the story of Mazoy. You can do it as well, guys. 100% for physical science at the end of the year. Stay with us, and we'll make sure that you've got as much practice as Mazoy got from us as well. And we'd love to hear from you. Post, talk to us, be part of the team, and be a mindsetter. We're going to a break right now. Welcome back, Grade 12s. This is Learn Extra Physical Sciences. We're talking about organic reactions. Now, guys, we've got a challenge question coming up very soon, and the first person that gives us a positive, correct response will get this calculator. So I'm going to post it in a second onto the Facebook page. Phil's going to introduce it, but I'm going to hand over to him. Get in touch, post any other questions that you've got onto Facebook, or follow me on Twitter. It's at Learn Extra. We'd love to hear from you. Phil, over to you. Take it away.
Thank you very much, John. Okay, well, welcome guys, and we're going to be talking about our organic reactions, and as John said, this stuff is absolutely fundamental. There is a lot of sort of questions, and now it's almost a third of your paper. If you analyze your papers, organic chemistry is around about a third of that chemistry paper too. Now, one of the things that you can start to do is to spot the patterns. What I'm going to try to do today is actually run you through the different types of organic reactions. We're going to be talking about addition, elimination, substitution, and combustion. Now, these 4 types of reactions you can actually identify very easily if you identify those patterns. I'm going to break it down into some pictures. We're going to take a look at some examples, and hopefully that challenge question becomes clear to you. Now, your challenge question, I'm not going to tell you which type of reaction it is, but I want you to start trying to see, are there any clues as to what type of reaction I have? Is there a difference in the number of reactants or products, or the type of reactants or products which I make in each one of these? I'm going to be pointing them out as we go. We're going to start off just by posing that challenge question. That challenge question doesn't actually specify which type of reaction it is, but I want you to use your wits, I want you to use your knowledge, and hopefully as the question goes on and as the show goes on, you can actually figure this out for yourself. So let's go to that challenge question, let's see what we're doing, and let's go forward to that. Okay, now the challenge question, I'm sure that John is putting it up on the page as we speak, and we're going to be putting these up, and there's 5 options. I'm going to be running you through my challenge question. I'm going to be showing you how to do this, and I'm sure that my producer is going to put this up on the screen, and we're going to show you exactly what's going on there and how to answer this question. So our challenge question for today asks you to identify the reactants. Now, our reactants could be anything. So what I'm going to do is I'm just going to circle what I want you to find. I'm going to see that the reactants over here, hang on, we haven't circled that properly. We seem to have a little bit of an invisibility problem there. Okay, but reactants are going to form something over here. Now this is 2-bromopropane. That's not what I'm asking though. That's a good naming exercise, but I want to know what are the reactants. I've got reactants which could be propyne and bromine. I could have reactants which are propene and hydrogen bromide, propene and bromine, propane and bromine, propyne and hydrogen bromide. Now there's a lot of words which sound very similar to each other. I want you to try pick out, is it A, B, C, D or E? I don't want you to guess. I want you to discuss on this Facebook page, and we're going to try to figure out what is going on here. I want you to look at your product, and I'm going to point out that there's only one product, and that should be a bit of a clue. I want to know which reactants can make this molecule on the right hand side. Now organic reactions don't have to be hard. So what I'm going to try to do is try to figure out what are the patterns and how can I find out what reactants made my product. So that's 2-bromopropane is my product. I want to find out how did I get there from my reactants. Okay, so let's get into the lesson. Let's try to figure out how to take down a addition, elimination, substitution, or combustion reaction. Try to figure out which ones are which and try to see the patterns. Now, the only way that you're going to figure out these organic reactions is if you simplify them down to some pictures inside your head. So what I've done is, you'll notice when I start to talk about my addition reaction, I'm starting to use shapes. Now, I've started to take a look at what type of compound I've got. I'm going to start off with this red block over here, which is an unsaturated compound. I'm going to be adding it to a white and a gray. So remember that addition, just like maths, and you can draw these shapes for yourself at home just to help yourself understand. When I do addition, I'm going to take an unsaturated compound like this one, add on something on the side, and we can actually see that the parts of this are going to be joining onto that molecule on the left. I'm going to leave them there for the moment, but you can see that when I move over to the right here, I've got a saturated molecule after this reaction. Now, I just want to emphasize what's going on here. A lot of you are taking notes at home. You might have not done the section at school yet. Some of you have, and you're just revising this. Again, I start off with 2 reactants, and I make one. One of them is unsaturated. This is a hydrocarbon of some sort, and I'm going to add it onto something else with 2 parts. And what happens is that all of these parts are going to become one molecule, which is more saturated than my reactants. So I've got an unsaturated molecule plus this thing with 2 parts. It all becomes one on the right-hand side. Well, that's fantastic, but it's kind of difficult. My molecules don't actually look this way. So what I'm going to do is I'm going to take an unsaturated molecule. I'm going to add it onto this thing with the 2 parts and then see what comes out. So I want you to draw this example with me. I'm going to go through it quite slowly just to make sure that people can follow, and let's see what comes out here. Now, I'm keeping the scheme up at the top here so that everyone can see what I'm doing. My unsaturated molecule over here, I hope that you can name it. I've got 1, 2 carbons, and this makes this ethene. Ethene is unsaturated. That means that it has a double bond. On the right-hand side here, I can see that my thing with 2 parts is bromine. I've got bromine and a bromine atom which can add to my ethene. Now, what happens when I unsaturate, or if I take an unsaturated compound rather, and I add something to it, I need to make place for it to make it saturated. So this bromine needs a place to live. If it's going to attach to the ethene, I want you to watch what happens to this part of the molecule. Something very strange happens to this piece of the molecule. I can see that the double bond cannot exist. I must break the double bond when I add my bromine, and out comes my product there. I've got 1,2 dibromoethane. Let me go through this again. Quite a difficult concept. I start off with a double bond over there. My bromine, 1 each, attaches to each carbon over there, and I form a product which has got the bromine and the bromine. Notice that there's a slight difference here. We've got no more double bond over there. I started unsaturated, and that shows me a double bond is unsaturated. A single bond is a saturated one. Now, this particular reaction which I've shown you is a very, very important test. This allows me to test for unsaturated compounds. Now, what I've got down at the bottom is actually a picture of how this is done inside the lab. Now, bromine has got a very particular color. It's red or orange, depending on which solvent you put it inside. So I can actually see that I've got some bromine. Now, when I put it inside the test tube, I can see if the red or orange color disappears. So I'm going to show you a picture, and you're going to tell me what's going to happen in each case. So when I take an unsaturated compound and I add bromine, something should happen. Either the red color will disappear quickly, or it won't disappear quickly. So let's take a look at that picture. On the left-hand side here, it's a little bit too small. I'm hoping my producer will put it on the screen for me. I've got 2 compounds. I've got one compound where I've added bromine, and you can actually notice that there's a small bit of red coloring down in the bottom. I've already added my bromine to this test tube. So bromine has gone inside here. I've already added my Br2 over there, and I'm busy adding Br2 to a second test tube. Now the second test tube is slightly different. The one on the left is hexane. The one on the right is hexene. So hexane means that I've got single bonds, and you can see that the red color is remaining. Hexene has got double bonds, and I hope that you can see, especially down at the bottom, that the color has disappeared. This means that bromine has been taken in, that addition has taken place. So let's just go through this again. If I add this red or orange bromine and the color remains, that means that I am saturated, like hexane. If the color quickly disappears, that means that there must be an unsaturated bond taking place there, or at least an unsaturated bond which is present, and that means that I've got my bromine which has disappeared. If the color goes, it's unsaturated. What do you think?
Well, that's an interesting question, Phil. Maybe you'd like to think about it while we go for a quick break. We'll be back straight after this. Check out the page. Make sure your answer's in. We'll see you in a minute. Grade 12s, welcome back. This is Learn Extra Live, and we're doing physical sciences tonight. We're into organic reactions. I'm not going to say much more. There are lots of responses to the challenge question on the page, and some of you have got it right, but I'm not going to give it away just yet. Phil, won't you help us get there? Take it away.
Absolutely, John. We've been doing really nicely on the show so far. Some of you are sending in fantastic responses to our challenge question. You're discussing some of the answers. Let's keep going. There's a couple more reaction types I want to show you. And the next one which I want to introduce to you is actually really easy. If you understand addition, remember that addition was taking an unsaturated plus something with two parts and putting them together. Now, elimination is the exact opposite. I'm taking a saturated molecule and I'm breaking it into two. Now, the word elimination means to release something or to get something out. So if I'm taking a saturated molecule, I can take these two small pieces and they can actually leave my molecule together. I want you to look at your notes about addition, and we're going to reverse them to talk about elimination. I'm taking a saturated molecule here and I'm making an unsaturated product plus another molecule which has got those two pieces which left. Remember that these two pieces must have come from somewhere and they can detach. So remember that those two can actually detach from each other. So what can happen is I can actually get them leaving my saturated molecule. But I'm going to leave them there for the moment. And we're going to take a look at an example of a saturated molecule undergoing elimination to become an unsaturated molecule plus another molecule. So I have one reactant which is saturated. I have two products. One of them is unsaturated. Now, in each organic reaction, I want you to concentrate. How many reactants and products do I have, and what type of reactants and products? So once again, one reactant, two products. Saturated becomes unsaturated. That's a sign that you've got an elimination reaction. So let's take a look at an example of an elimination reaction. And once again, I'm going to leave the diagram up at the top here just to show you what I'm talking about. A saturated molecule becomes unsaturated, and that little piece is leaving. Now, it's quite difficult to see when I take a look at my initial saturated molecule. Every time I show you an organic molecule, I want you to be naming it inside your head. Very good practice. It's just repetition, making sure you know your rules. So 1, 2 carbons gets me eth, single bonds gets me an, that OH gets me ol. This is ethanol. Now ethanol is saturated because I can see that there is a single carbon-carbon bond inside there. So this single carbon-carbon bond and the fact that there's only one molecule as a reactant shows me that I'm probably going to undergo an elimination reaction. So if I take my molecule over here, let's find out how to eliminate it. Let's see what can eliminate. Well, the easy target, if I don't know where to start, is the thing which stands out, and that's the OH. Now I've got an OH over here. That can be eliminated. The problem is that something on the other side of the carbon must be eliminated as well. Now, whenever we eliminate something on one carbon, remember that a double bond is going to form between them to make an unsaturated molecule. This is a lot of information to take in. So let me go slowly through this. I'm going to take something off the one carbon, but what about the other carbon? There must be something else which comes off. Now, I can see a lot of you at home are probably starting to put together the pieces here. If I take an H, an O, and another H off all together, and they come off as one thing, I can see that they're going to come off as one molecule. Remember that one from each will come off. Now, when they break their bonds to the carbons, that leaves space for a double bond between them. That means that we've made our unsaturated molecule, and I'm pretty sure you can guess what the other molecule might be. So let's bring that up. I can see that I've got my unsaturated molecule over here, and that my double bonded ethene. Now you can see that H and OH, you might want to write this out in a slightly different way. I'm going to do that with you. So H and OH, usually I write as H2O. This is water coming out. Now for those of you who are studying this, when water is leaving, I can see the water leaving my ethanol. This is dehydration. This means that water is coming out. Something else which they can ask you in a test or an exam is, how do I get dehydration to occur? Now, this is one of those reactions which has got a special catalyst. Now, whenever I'm trying to add or remove water, there's a special acid which can help me do that. And that is sulfuric acid, which is H2SO4. Even if you haven't done the contact process, even if you don't know what sulfuric acid is, H2SO4 is your friend when you're trying to add or subtract water. It depends on the conditions. Now this one, I want the H2SO4 to be very, very hot. That means that the water will boil off as a gas and I can remove it very, very easily. My ethene will come off as a gas, my water will come off as a vapor. I've undergone a dehydration reaction. I took a saturated molecule, it became unsaturated, and something else came off as a separate product. I hope that you can see the pattern occurring inside there. Once again, I've got my single bonds making this a saturated molecule, my double bonds making this unsaturated, and it becomes water as a result of this. Now, I want you to try practice this. Try see if you can come up with your own elimination reactions. Now, I think it's time for another very short ad break while I get my next set of reactions ready. Okay. What do you think, John?
Yeah, let's go for it. Just one question though, elimination reaction, dehydration, an example of that? I mean, I know you've been doing it here, but isn't that the one where we put sulfuric acid and sugar and it makes that carbon come out?
Okay, absolutely. An example of a saturated compound which is present inside your food, present inside lots of things, inside plants, inside starch, is actually glucose. And glucose is an alcohol. It's a carbohydrate. Now, I've got water which is available on that. That word, carbohydrate, means that I've got carbon and water present on there. If I put H2SO4 on glucose, what's going to happen is it's going to dehydrate it, leaving that carbon behind. And that's that experiment where we've got a large black mass actually coming out. That's the carbon left over once we've taken the water away. Very nicely spotted, John.
Thanks, Phil. Right, let's go to that break and we'll be back with you straight after this. Welcome back, grade 12s. We're doing organic reactions. Now we've done addition. We've just completed elimination. Phil, what's up next?
Absolutely. John, we are taking a look at substitution. Now, substitution is the swapping out or the changing for something which is there. Now, you might have heard of this word, a substitute, it means that something has taken the place of something else. Now, substitution, you might have heard of this at school. A substitute teacher is a teacher which takes the role of a normal teacher. Now, in this case, I'm actually taking pieces of molecules. Now, a lot of you are actually drawing these diagrams at home, and we appreciate that. So I'm going to go slowly so that you can take these notes down. Now, one thing which stands out to me for substitution is that there's 2 reactants and 2 products. That's quite important. And one of the things that really stands out to me is I started out with a saturated molecule. I ended up with the saturated molecule once again. It's quite important to note that I started and finished with a saturated molecule. The question is, how? What swapped place? Now, if you take a look at your shapes, take a look at the red, what it's combined with. The red had a blue, sorry, not a blue block, it's looking blue in the studio here, a white block which is attached to it. What happened to that white block is the white block moved to my green triangle. The gray circle took the white block's place. So what happened was these two actually switched place. So what I can find is that my white block moved and my gray block switched around and moved into its place. So that's what actually happened. I'm going to leave it in its original place. So if you're taking notes, that it's in its correct place. So what happened was the white part of the molecule, whatever that was, traveled across to a separate molecule. The gray moved into its place. And I hope that you can see that inside my product. Now I've got a red block with a gray circle. I've got a green triangle with a white block. I hope that you can see that there's been an exchange. They've swapped partners with each other. This white block can be anything. It can be a hydrogen, it can be a halogen, it can be a hydroxyl in the case of alcohols. It can be virtually anything. Anything which can be swapped out or changed for something else can be substituted. Now I'm going to take a look at another example, and we're going to keep that diagram up there, and we're going to see. Now the reason I've chosen not to hide these is because I want to demonstrate where the pieces of the molecule go. Now this can be quite tricky. So what I'm going to do is on the left, I'm actually going to highlight what represents the red block. So my red block was my saturated molecule with something joined on. So I'm actually going to highlight it here. Here we go. Let's see that we can see. There is my red block. I'm sure that you'll notice that there's something which is stuck on the side here. My hydrogen. My hydrogen can actually leave. Now this one requires a little bit of special conditions. Now this is something quite special. This doesn't happen very easily. Saturated molecules don't undergo a reaction with bromine very easily. I need to help it along. But let's keep focused for the moment. Let's see what's represented by green and by gray, and we'll try to see what happens over there. So I'm going to represent green over here. Here is my green triangle, and that was the one bromine. I'm sure that you can see that my circle, now I don't want to put gray on here because you can't really see it, but it's the only circle there. I can see that bromine is waiting to be swapped out. These pieces can switch places with each other. Now, let's turn our attention to what happens when the hydrogen and the bromine switch places. You can see that on the right-hand side, now I've got a bromine, which is sitting over here. My bromine was my circle. I can see now that there's a combination of a bromine and a hydrogen, which there never was before. Remember that bromine was our green triangle. It stayed where it was, but it got a new partner. It got a new friend. So I'm just keeping the shapes the same so that you can actually identify from my picture what is going on. Now, where did the red block go? It's still there. The red block remained exactly where it was. Now, substitution is one of the trickiest ones because there's carbons and there's hydrogens everywhere. So we take it and we look and see what didn't change and what did change. So what is the pattern? I've got ethane with its extra hydrogen. That's the hydrogen that's going to be swapped out. So let's identify which one swapped places. So let's do that in a different color, not to confuse things. Let's pick that. Right, I don't want to be working in white because everything else is here in white. I can see that these two are actually swapping places. The hydrogen and the bromine are going to swap places with each other. But now there's a problem with this type of reaction. I told you that alkanes, saturated molecules, were very unreactive. They cannot react very easily with bromine. And I told you that bromine remains its same original color when I mix it with an alkane. So how is a reaction taking place? Well, it needs a little bit of help. I need some help to start off this reaction. I need to break up the bromine and get the bromine all excited. I need to get it radicalized. I need to break it up into two pieces. Now, you don't need to know that detail, but you do need to know where does this energy come from. Now, if you're watching Tracy's show a little bit earlier, Tracy was starting to talk about light possessing energy. Now, the particular light that I need to possess this energy is called ultraviolet or UV rays. Now, the best place that I can think of to get UV rays is sunlight. I can get a whole bunch of UV light from sunlight, and this is why you have to protect your skin. Sunlight can actually cause reactions inside your cells which are not desirable. Things which age your skin, things which cause cancer. Now, UV light is some pretty bad stuff. John, looks like you got a question.
There was just a question from Anele. She wants to know what happens to the bond. And I think you're going to get to that right now.
Absolutely.
So let's go to it.
Okay, very nice question, Anele. The question is, what happens to these bonds? Now, in addition, I was taking something which was unsaturated, breaking the double bond and making space, and we were going to saturate it. In elimination, we were going in the opposite direction. Now, I'm actually going to redraw this and sort of diagram it out. What actually happens to this bonding? Now, let's just make a little bit of space, and let's see what happens to this. Okay, well, starting off with my ethane. I started off with ethane, which was 2 carbons, with my hydrogen, which had its bond over there, and we've got all our hydrogens, which are still in place. Now, I'm going to highlight the parts which are going to switch. Now, the thing that I find particularly interesting is this hydrogen over here is attached by a covalent bond, a very strong covalent bond. Now, if I activate bromine by turning it into a radical, this is bromine without a friend. This is bromine which is angry with the world and wants to get a bond from anywhere. What I'm actually going to find is that bromine is able to steal an electron out of that bond. What happens is that electron from that hydrogen is stolen by this bromine. What that leads to is something very, very odd. Now, initially I had bromine which had this unpaired electron. Now, you've seen this in Lewis-Dots diagrams where I've got an unpaired electron. All they want is another electron. So I've still got this bromine radical. This was caused by the UV light. Now, this is detail which you don't need to know for your exams, but it's interesting for those who are A candidates. So I've got my hydrogen here. I've still got that empty spot over there. I've now got a carbon radical, which is very unhappy. I've got a carbon that has had its hydrogen stolen away from it. I've got my H and my Br. Those two will live happily with each other, but I've still got another bromine, which is unpaired. Now, what happens and how we make our product is I actually find that these two are going to make their own pairing, and we're going to make our product. I hope that answers Aneli's question.
Yeah, I'm sure that's really great. I think it's time for a break. So let's go to it. It's a short break, and then we're coming back to combustion.
Absolutely.
Okay, cool. We'll see you after this. Grade 12s, welcome back. We're doing Learn Extra Live, and it's organic reactions, one of my favorite parts of chemistry. And we've been going through addition, substitution, elimination, and we're now going to go to combustion reactions. So Phil, please help us out.
Thanks so much, John. Now, what you're going to be seeing is how we combust or how we burn objects. Now, this is a very common and very, very easy exam question if you know how to balance a chemical equation. Now, combustion can occur to any number of organic compounds. It can occur to a saturated or an unsaturated compound. The problem is that there are 2 reactants and 2 products. But what gives this one away is which reactants and which products. So a couple of the things that I want to highlight, some things that are very, very important. Oxygen is one of the reactants. I need oxygen for combustion. Remember that combustion is also sometimes called the burning. Now, sometimes I call the organic compound which I am burning, sometimes this is called a fuel. Now, you might have heard this word before. This is anything which we can mix with oxygen to obtain energy. Now, some of the exam questions have actually asked, why is combustion a very useful reaction? Now, combustion is very exothermic. Now, for anyone that doesn't remember what exothermic means, it means that this reaction can give us lots of usable energy. Now, one of the other products of this is not actually a chemical, but is energy in the form of heat, and it can be light, and it can even be electricity if you put it inside a certain chemical reaction. Now, a fuel plus oxygen gives us, now these are the 2 products which show me that I've got combustion. I've got carbon dioxide and I've got water. Now, it's quite easy to understand where these products come from. I'm burning a hydrocarbon, lots of carbon and lots of hydrogen. When I combust a hydrocarbon using oxygen, oxygen will join onto the carbon and will join onto the hydrogen. So carbon dioxide and water are my products. Now, these two should be very, very familiar to anyone that's done up to grade 9 natural sciences. Now, that should be all of you because you're doing physical sciences in your senior grades. Carbon dioxide and water are the two things which I give out when I exhale, when I breathe out. Now, the very same reason that I'm giving out carbon dioxide and water is that a type of combustion is actually happening inside your cells. Now, anyone doing life sciences tomorrow, I want you to take a look at cellular respiration, where oxygen is taken inside the cell, carbon dioxide and water is going to be spat out of the cell. What's happening is I'm burning the fuel inside my body to obtain the energy which I need to live. Now, I can make use of this reaction. I can take a fuel, just like petrol or diesel, and burn it using oxygen to make my carbon dioxide and water and energy to drive cars, drive trains, drive trucks, and drive transport and industry. The burning of hydrocarbons can even create the electricity which you need to watch this show at the moment. So if I take that fuel and I burn it in oxygen, I'm going to make my two products and energy. One of the questions which can be asked about this particular type of reaction is, what is one of the negative impacts of combustion? Well, we can list quite a few. One of them is one of these products. And this product over here, carbon dioxide, is relatively non-toxic. It's not poisonous. However, it's a greenhouse gas. Now that means that this gas is capable of trapping the Earth's heat and not letting it out. Now, a greenhouse gas contributes towards global warming. Now, be very, very careful. If you use this in an exam question, I've got to state this very, very clearly, is that carbon dioxide is just a greenhouse gas. The trapping of the heat is global warming or climate change related. So, if I take my greenhouse gas over here and I pump it into the atmosphere by burning these hydrocarbons, I contribute towards climate change. One of the other problems is that the fuel itself, like oil and natural gas, now a lot of you might not realize this, is that oil and natural gas are running out. They are fossil fuels. That means that they can only be created over millions of years. So oil itself, if I burn it all up, I'm going to run out of this stuff. The prices are going to go up. I don't know if you've noticed that petrol is going well over 11 Rand a litre, and that's because the oil is running out. Another reason is that they're starting to add things like carbon taxes. That's because these greenhouse gases are going to be taxed in the future. When you purchase a vehicle, you actually get taxed on how much carbon dioxide is given off by this combustion. But let's get into the reaction. Let's see if you can balance this. Okay, so what I'm going to do is I'm going to choose an example, and I haven't completed the example for you. I'm going to take a saturated molecule over here, and I'm going to burn it in some oxygen, make carbon dioxide, and the other product, water. The one which I've chosen, I hope that you can name this, 3 carbons, 8 hydrogens, 3 means prop, and because there are 2n plus 2, that means that I've got an alkane. Now that's not the important piece. What I'm going to do is I'm going to show you a couple of tricks on how to balance one of these reactions. I've chosen this one because it's particularly tricky. What I've got to do, first of all, is inspect my reaction. I can see that there's oxygen in 3 out of these 4 compounds, so that's a bad place to start. What I'd like to do is leave oxygen until last. Here's the trick to balancing a combustion reaction. So I'm going to take my carbons and try balance those first. I've got 3 carbons on the left. I should have 3 carbons on the right. I have 8 hydrogens present inside my propane on the left. I should have 8 on the right. Now, because water has got 2 hydrogens inside each molecule, that gets me 4 water molecules. Now, I've balanced my carbon. I've got 3 on each side. I've balanced my hydrogen. I've got 8 on each side. Let's take a look at the oxygen. Well, at the moment I've only got one oxygen molecule. Now let's see how many oxygens we've got. 3 multiplied by 2 gets me 6 oxygens. So I'm just going to make a little bit of a note over here. So I've got 6 oxygen atoms over there. So that looks like 60, but it's actually 6 oxygen atoms. And over here, I've got 4 oxygen atoms over there. So 4 plus 6 will get me 10 oxygen atoms. So what I'm going to do is just take that away because that's a little bit messy and misleading. But I can see that I've got 6 oxygen atoms over here and 4 over there. If I add that all up, I get 10 oxygen atoms. How can I get 10 oxygen atoms on the left? Well, that's quite easy. If I've got them arriving in pairs, that means that I will need 5. Now, I need to double check myself always. 3 carbons on the left, 3 carbons on the right. 8 hydrogens on the left, 8 hydrogens on the right. Check my oxygens. I've got 5 times 2, which gives me 10. 3 times 2, which gives me 6. And 4 times 1 gives me 4. And 6 together gives me 10 oxygens. So I've got 3, 8, and 5 times 2, which gave me 10 oxygens. So everything seems to be balanced. I've got the same number of carbons as I do on the right-hand side. The hydrogens balance out. Remember to leave the oxygens until last. If you want a little bit of a challenge, one thing that you can do is actually try burn propene. That makes the oxygen a little bit more challenging. So what we're going to do, John, any questions?
Just one question quickly before we go to break. This is for complete combustion, hey?
Absolutely.
There's a trick there, and I'm sure we'll pick that up after the break. Just think about it. We have to make sure it's complete, but we'll go to a break first, and we'll pick it up after the break. See you now. Grade 12s, welcome back. Learn Extra Live, and we're doing organic chemistry this evening. So we're going through the reactions, and we've finished, I think, the addition, substitution, elimination, and combustion. I think it's time to get back to that question that you've challenged us with, Phil.
Absolutely, John. I just wanted to make one last note on this combustion. Somebody actually sent it in, and you mentioned it a little bit before the break, that CO2 was actually only a product of complete combustion. Now, one of the things that they can do to surprise you is if we get incomplete combustion. That means that there's not enough oxygen when it's burning. Now, you could have a substance called carbon monoxide being formed. So that very often could be thrown in there. So CO, carbon monoxide, could be the product of incomplete combustion. Now, I think it's time to go to that challenge question and put people out of their misery and hopefully make some people happy and get some other people some work to do. Okay, so there it is. I've gone back to my challenge question. Here it is. Now, this should be your clue. Now, I've got reactants. That means that there is more than one reactant. So that's one of the clues which I gave you. So I have more than one reactant. Now, that's one of the clues that I should be getting. Now, there's a problem with this, that A through to E has got more than one reactant. So that doesn't really tell me which option. However, the fact that there's 2 reactants completely wipes out the idea that this might be an elimination reaction. Also, another thing which gives me that clue is that I've only got one product. Only one product. That should be shouting to you that this is an addition reaction. I've got an addition reaction making only one product. So if I take a look at this thing, it's only one, and I find that it's saturated. My product is saturated. That should be a very big clue. Addition produces a saturated compound and only one product. That helps me find out what type of reaction I must have done. Now the question is, how do I trace this back? How do I find out what type of reactant might have made this product? Well, now if I know that addition is the adding of something small, let's try an elimination reaction on my product and try to figure out what my reactants might have been. So let's try to trace it back. If I've got 1, 2, 3, and I've got a bromine, now let's try to see if we can't do an elimination reaction to try to find out what the addition reaction might have looked like. Remember that addition and elimination are the exact opposites of each other. So let's try and go backwards. Let's try and figure out what is extra on here. So this should actually tell us which my reactants were. Now, remember what I told you. When you do an elimination reaction, that is the reverse of an addition reaction, I try to find out what is new. Well, the bromine looks to me like something which is special. Now, if I want to find out where this bromine came from, well, there's two places it could have come from. But I know that it came from an addition reaction. That means that something else came with it. So what I'm going to do is I'm going to figure out what else on this molecule could be there. Now, a lot of you might be asking questions about this. I'm going to ask John in a second. But I've got hydrogen and bromine which might have been added onto here. So let's pull them off and let's see what's left over. So I'm going to draw the molecule without the H, without the Br, and we're going to see what should be there. So I hope that you can see that there's something missing. There's something not quite right about what I'm drawing over here. I've got a hydrocarbon over here where I've got my two carbons which are in place. I've left out the hydrogen and the bromine, but that means that there should have been a double bond. There we go. We've got our double bond, we've got our other reactant which is in place there. So, let's quickly name them, let's find out which option was correct. I'm sure that there's a whole bunch of you already screaming it at home and trying to figure out why you didn't get it in the first place. I know a lot of people thought it was the one option, but I'm going to discuss why it wasn't the other option. Now, I misled you with some of these options. So here it is. 1, 2, 3, which is prop. There's a double bond in there in the first spot, so that's propene. Over here, I've got hydrogen bromide. That's my other reactants. Now, lots of you have already got that answer from me saying that, so I've got propene and hydrogen bromide. If you take a look at your options over here, there it is. Propene and hydrogen bromide. Now, I'm going to discuss some of these other answers with you. Are there any questions about this so far?
There was one question earlier, which was about why is the bromine on position number 2?
Excellent question. Very, very good question. Okay, now, if I'm doing an addition reaction like this, how do I know whether or not the bromine should be on the end carbon or on the middle carbon? In other words, the primary carbon or the secondary carbon. Now, those are words which you might not have heard before, but I know that this first carbon is only bonded to one other carbon. That becomes my primary carbon, and that's how I show it. A 1 with a little degree sign next to it.
Sorry, Phil, is that just like primary and secondary alcohols?
Absolutely. Primary and secondary alcohols talk about the OH being on the first carbon, in other words, the end of the chain, or somewhere inside the chain where this carbon is linked up with two other carbons. Now, you've got to take a look at the thing which you're joining on and decide which one's going to join onto which. Now, there's a very easy rule. You don't have to remember the name of this, but I'm going to show you how to do it. It's called the Markovnikov addition rule. Now, that's a real mouthful, and I'll write it down. If you want to do a little bit of searching on yourself, you can find out what Markovnikov said about addition. But here's an easy way to figure this out. The bigger of these two is always going to prefer the carbon with a higher order number. That means that this big part is going to prefer the secondary carbon. So I'm going to tell you that bromine, because it's more hungry and it likes carbons with more friends, I'm going to find that bromine likes to join onto a secondary carbon. Hydrogen likes to join onto a primary carbon because it's the smaller of the two. The bigger one goes on the carbon with the most friends inside the chain. Hopefully that answers that question.
Great, thanks.
Okay, now other things which you could add onto here. Now, very often you can add lots of other things, and other things which you could add on if you wanted to add water, in other words, to hydrate. I like to draw water into two pieces. I hope that you can see if I took propene and I added water, there would be two potential products. I would get propan, 1 ol, and propan, 2 ol. If you want to challenge yourself and apply the Markovnikov, and I'm going to write this out, Markovnikov, okay, it's a Russian name. So Markovnikov decided how addition takes place. Now, if I did Markovnikov addition of water, which is H and a OH, what we would find is that if I added water, I would get propan 2-ol. So if I apply Markovnikov's rule, again, you don't need to know this name, but if I applied that to my propene, I would get propan 2-ol, and there it is. I think we're running a little bit short on time, John. I'm not sure. Is there time for one more little question?
I think, yeah, short question. I just need to find you the one. Guys are still struggling about the issue between saturated and unsaturated. Why don't you just quickly just go over that again?
Absolutely. Okay, the thing which stands out over here, my product being saturated. How can I say that my product is a saturated compound? One of the things that I must check for a saturated compound is these things inside the middle. I must look at the way in which carbon is bonded to other carbons. I can see that carbon is only bonded with other carbons using single bonds. However, when I've got something which says ene or ine, this means that I've got double and triple bonds, and double and triple bonds mean that I've got space to add things on. Ene and ine, you can see them all the way through here. That means that I'm unsaturated. John, I think that's all we have time for this evening.
Yeah, I'm just quickly trying to check who was the first person to give us the correct answer. And I did see it, and then I've lost it. Now, there have been a whole lot of people that have given us great explanations, amongst them Tabang, and there were a couple of others. But we'll notify you who the actual winner is, who was the first person to give it. We'll take that down. I just want to remind you, we're on for Life Sciences tomorrow, so join us for Life Sciences from 4 o'clock all the way through to 7 o'clock. Kathy will be here, and then we're doing a live show on Saturday morning from 10:30 till 12 o'clock. So join us, revision of Term 1. It's been great to be with you this evening, and thanks, Phil, for your explanations. I've really enjoyed it. Guys, from us at Learn Extra, bye for now.